The talk is being presented from the unceded territory of the Seminis First Nation on Vancouver Island, Canada. This is the first of a series of 3 talks on climate change and global warming. And I put these talks together prompted by a personal need to, first of all, understand all the terms that you hear bandied around, get beyond the rhetoric of obviously biased parties, and to take a look at the evidence so I can come to my own conclusions as to the realities of global warming. Is it man-induced or not? And how I need to react to it in my everyday lifestyle. I'm going to try and present the information in an unbiased and impartial manner. And it's up to you to decide whether I've managed to do this. And it's also up to you to decide what to do with the information. I'm not a climate scientist, I am a geologist. So there's a bit of a caveat there. The talks are a compendium of the work of others. The information and most of the illustrations were taken from the internet, and I post the links to where I got the information from. The quote at the bottom of this slide, there are some people, if they don't already know, you can't tell them. I include this to vaguely emphasize that climate change is a hot topic with plenty of adherents to vested interests who are remarkably resistant to considering information that belies their stance. So why 3 talks? Well, partly because climate change is such a vast topic and I couldn't do it justice in a single presentation, well, not without losing you and boring you. So I broke it down into 3, each one about 45 minutes long. The first talk is aimed at putting current global warming into perspective. Titled Causes and History of Climate Change, I review what controls global climate and what controls global climate and the history of climate change as evidenced in the Geologic Record. This sets the stage for the second talk, Global Warming Realities, Causes and Cures, in which human impact on climate change is examined. The international climate accords are discussed in relation to global warming forecasts, agreed policies to minimize global warming and their effectiveness. And also Canada's environmental policy and role is put into perspective. The third and last task, Effects of Global Warming, explores the impacts that recent global warming is having on the world around us, with particular focus on Canada and British Columbia. Let's start with some important definitions. First, we need to understand what we mean by weather and climate. Weather is what conditions of the atmosphere are over a short period of time, i.e. days and hours. Climate is how the atmosphere behaves over a relatively long period of time, i.e. decades or longer. And climate change refers to changes in the long-term averages of daily weather. Global warming is a defined trend of increase in the average temperature of the atmosphere at the Earth's surface, especially a sustained increase great enough to cause changes in the global climate. And finally, anthropogenic global warming, shortened to AGW, is a mouthful term which you might hear. It refers to the theory that human activities, especially those since the beginning of the Industrial Revolution around 1750, are resulting in an unprecedented and unnatural global warming trend. The word anthropogenic means basically coming from humans. The greenhouse effect, this is, I'm sure you've all heard about this. It's the warming of the atmosphere by trapping of radiative energy by what are called greenhouse gases in the atmosphere. Climate change prior to the COVID-19 pandemic was the crisis affecting mankind. Sensationalist headlines scream environmental destruction and of us along with it. Countries point fingers at the bad guys, with the fingers generally pointing at someone else. The discussion has become intensely politicized. Like the atmosphere, the debates become heated. Protests become violent. Most politicians with the power to shape a nation's climate policies have little or no scientific education. Many risk being swayed by political and financial pressures rather than scientific truths, which are longer term in their effects than the next election. we as global citizens need to understand for ourselves what all the fuss is about, rather than being swayed by those who speak loudest. Who and what to believe. This is pretty well everyone knows who this famous climate activist is, Greta Thunberg. Here's a clip of her at the UN earlier this year with a message about climate change.
People are suffering, people are dying, entire ecosystems are collapsing. We are in the beginning of a mass extinction, and all you can talk about is money and fairy tales of eternal economic growth. How dare you?
Well, those are strong words indeed. But Greta is not doesn't have the only perspective, however. There are people who say that climate change and global warming are hoaxes. Here are some quotes from a particularly prominent climate change denier, Donald Trump. The concept of global warming was created by and for the Chinese in order to make US manufacturing non-competitive. Give me clean, beautiful, and healthy air, not the same old climate change, global warming bullshit. I'm tired of hearing this nonsense. And when will our country stop wasting money on global warming and so many other truly stupid things and begin to focus on lower taxes? So who to believe? Do we believe the variably peaceful and at times anarchistic protests of Extinction Rebellion? Or the industrialist who says, everything's fine, just keep buying our products and we'll keep producing them? Or do we believe the climate scientists, some of which are accused of cooking the data and stacking the scientific review process such that only environmentalist man-induced climate change advocates' work gets published? Do we believe the information which we, the public, are fed, some of which is demonstrably tainted by bias and self-interest? Or do we believe the influencers on social media who trash detailed scientific work with just a word, saying it's all wrong? What I'm trying to do in this talk is focus on the real data, the clean data, climate science. Let's hope I can do that. Some key points I'd like you to take away from this series of talks. First of all, climate change is a naturally occurring continuous phenomenon. Secondly, factors influencing climate change are varied and complex. It's arguable how well we understand those complexities. Greenhouse gases in the atmosphere trap energy in the form of heat. Human activities are increasing the concentration of greenhouse gases in the atmosphere. The atmosphere is warming at an accelerating rate. The degree to which human activities are contributing to this warming remains a point of significant debate. Regardless of that, global warming effects are here to stay, and we need to take appropriate measures. Modeling of future climate change is complex and controversial. But above all, at the end of these talks, you have to decide what your role is in all of this. Let's start our investigation by taking a look at factors affecting the Earth's climate. Our climate results from the distribution of heat around the planet. A small amount of this heat comes from radiation from the molten interior of the planet, but the vast majority of energy that turns into heat on the Earth reaches the Earth from the sun in the form of electromagnetic radiation. So when we consider the Earth's climate, we really need to take into account the interrelationship between the Earth and the sun. And these are the extraterrestrial factors that referred to in this slide. Extraterrestrial factors to consider include solar output. In other words, how constant is the output of energy from the sun? Interstellar dust. Does the existence of vast clouds of interstellar space dust through which our solar system passes as it moves through space affect the amount of energy arriving at the Earth from the sun? And lastly, in the extraterrestrial factors, does the geometry of the Earth's rotation around the sun and around itself affect the amount of energy arriving? we also need to look at factors on Earth that could potentially influence climate. Terrestrial factors affecting the Earth's climate include volcanic emissions, the degree of volcanic activity with associated emissions of vast amounts of carbon dioxide, sulfur dioxide, and volcanic ash into the atmosphere. Mountain building and continental drift, these are long-term for sure, but changes in distribution of the Earth's land masses due to plate tectonics resulting in continental drift and mountain building. These, through time, fundamentally change the pattern of oceanic and atmospheric circulation, and we can expect to see effects in the geologic record associated with that. Surface reflectivity, in other words, the amount of snow and ice in the polar regions and the amount of clouds in the atmosphere which reflect energy incoming from the sun back out into space. Atmosphere-ocean heat exchange, referring to ocean currents and wind systems. And atmospheric chemistry, the chemical and physical makeup of the atmosphere. In the following slides, we'll take a look at many of these factors and try to consider their importance to climate change. All right, yeah, better get used to it. There's going to be a number of graphs in these talks, but they're actually pretty simple to understand. We're going to start looking at solar energy output and whether it's variable or not. And if it's variable, if there's sufficient variation to produce climate change on Earth. In this graph, what we've got is we've got time along the horizontal axis at the bottom. And we're spanning a time frame from the year 1880 to 2020, today. There are two vertical axes to show different trends through this time period. The axis on the left, colored in blue, shows the amount of energy being radiated from the sun. This blue line, which we see wiggling along here, is the amount of energy received from the sun during the time period graphed. And we can see there is variance. And when we look at this, we think, oh, there's quite a lot of variance. But if we actually look at the scale on the left, the amount of variance in the energy emitted by the sun during the 140-year period graphed is about 0.036% variation. So in effect, over this 140-year period, it's pretty well okay to think about the amount of energy coming from the sun as being constant. What very minor variation that we see in this graph is likely due to the sun's internal convection patterns, which are manifested in sunspot cycles. The vertical axis on the right, in red, shows change in the average atmospheric temperature compared to a pre-industrial revolution standard. And that's shown in the axis as 0. The red line shows that the Earth's atmospheric temperature is going up. This warming trend picking up significantly since about 1970. So on the face of it, from this graph here, we see that there's no obvious connection between warming of the Earth's atmosphere and what little variation of energy is being emitted from the sun. If anything, the graph shows the opposite since about 1980. In other words, the atmosphere is heating up while the amount of energy from the sun is going down. So there's no clear evidence that any changes in the amount of energy being emitted from the sun has an effect on the Earth's climate. So what about our solar system passing through clouds of interstellar dust? This is an image taken from the Hubble telescope, which shows a cloud of interstellar dust, a huge cloud of interstellar dust with stars inside and out of it. And remember, our sun is a star. If your solar system was inside this cloud, the effects would be something like shining a light through fog, i.e. less energy that is radiated from the sun would be reaching the Earth. Now, while this effect is real, its duration would be extremely long-term, so it's not a consideration for us in this series of talks when we're focused on climate change, global warming within, say, the last 200 years. We noted earlier that the majority of energy expended as heat in our atmosphere comes from the sun. We've seen that the energy output from the sun is pretty constant. So what we need to look at is the interrelationship of the Earth and the Sun to see if changes in this relationship might affect the amount of energy arriving at the Earth. This slide is a depiction of our solar system. It's not drawn to scale. But what it shows is the Earth as the third rock from the Sun. Anyone remember the TV show? Our planet rotates around the Sun once every year. And as it does so, it receives energy radiating out from the Sun. Although the circumnavigation of the Earth around the Sun in a year is shown as a circle on this slide, in fact, that's not the case. It's not a perfect circle, and we'll take a closer look at this. The rotation of the Earth around the Sun is actually in the form of an ellipse. Here's the Sun, and here's the Earth rotating around it. The shape of the ellipse changes predictably through time. And the form of this ellipse change occurs over hundreds of thousands of years, but in a predictable manner. And this is called eccentricity. The closer the Earth is to the Sun, the more energy it receives. The further away it is, the less energy it receives. So this elliptoid circumnavigation of the Earth around the Sun affects the amount of energy and hence could be expected to have an effect on Earth's climate. Now, while the Earth rotates around the Sun in this slightly eccentric fashion, the Earth itself rotates once every 24 hours, one Earth day. And this is easy for us to understand because we're very familiar with it. But you may or may not know that the axis of the Earth's poles is at a slight tilt from vertical, and that this tilt varies through time, and it actually oscillates between 21.5 and 24.5 degrees from vertical. And this oscillation cycle takes about 41,000 years. The changing tilt means that the attitude of the Earth toward the Sun changes through time, and this affects where incoming radiation from the Sun hits the planet. Another complicating factor is that the attitude of the Earth toward the Sun also changes through time. In other words, the planet wobbles in a predictable manner, just like a spinning top before it loses balance. Each wobble cycle takes between 19,000 to 24,000 years. This is called precession. And look, I know it's a bit complicated to try and think of this all in one time in our mind, but really what you need to remember is that the Earth's movements around the Sun and itself result in predictable variations in the amount and intensity of energy arising from the Sun. We'll come back to this in a little while. So we've looked at all the extraterrestrial factors affecting climate. Let's now turn to the terrestrial factors, i.e. those on Earth which affect distribution of the energy from the Sun around the planet. Some of these factors are very long-term, and this is a long-term one. Since the Earth's crust formed about 3.8 billion years ago, the land masses on the Earth have been moving around in relation to each other in a process which is called continental drift. Through geologic time, the changing distribution and size of land masses affected reflection of the Sun's radiation and the oceanic and atmospheric circulation. This slide shows changes in the distribution of the Earth's landmass over the past 120 million years. Bottom left, the early Cretaceous world of 120 million years ago, before the opening of the North and South Atlantic Oceans. Obviously, there were very different oceanic and atmospheric circulation patterns than those of today. So moving over to the right, the Eocene, 50 million years ago, this map looks a bit more familiar, more similar to today, but there are some important differences. Look where Europe is now. Africa is approaching Eurasia from the south, but no collision has taken place yet. And India is making its way north. So there's lots of ability for east-west water movement north of Africa. And the Alps and Himalayas have not yet formed, so there's no mountain chains to break north-south wind circulation patterns. Top left, the Miocene, 20 million years ago. You have to look a little bit harder to see differences from the present day, but there are some important ones. There's an open seaway between North and South America, for instance, and more of Europe is underwater. So, and of course, top right here, this is the present Earth today. So you can imagine the significant effect that changing land masses and mountain chain distributions have on ocean currents and wind patterns over long periods of time, and that this effect would have had a change of distribution of climatic belts through the Earth's history. So this map of the Earth today with our current continental configuration shows the global pattern of oceanic circulation. The oceans collectively act as a major heat distributor around the Earth. There's a distinct relationship between the pattern of ocean currents and the distribution of land masses. The oceanic circulation system consists of shallow warm currents shown in red here and deep underlying cold currents shown in blue. The entire oceanic circulation system takes about 500 years for a complete circle. One part of this current system of significant concern today is that part in the Atlantic Ocean. What we're looking at is here in the North Atlantic Ocean, we have a warm current coming from the tropics, basically, which brings warm water across to Northwest Europe. This is called the Gulf Stream. This whole system here is extremely important and in keeping Western Europe with a mild climate, mild maritime climate. This warm water comes up from the Gulf, along the Gulf Stream, across the Atlantic, warms Western Europe, comes down, and as it circulates toward the east coast of Greenland, it cools and sinks and then returns back down to the southern hemisphere into the circumantarctic system. So anything that would affect this oceanic circulation will have a profound effect on northern hemisphere climates. The other great global heat circulation system is in the atmosphere in the form of winds. There's a defined pattern of wind on either side of the equator, all to do with distribution of heat, as warm air from the tropics moves out and cold air down from the poles. This distribution of winds was, of course, well known in the days of sail, as the name trade winds testifies. The satellite image on the lower part of the slide, dating from 2005, beautifully shows the wind patterns named in the diagrams above, as exemplified by cloud distribution. With the winds, there's also very important redistribution of moisture, and we can see this in the images as cloud formations. The clouds also act importantly to reflect incoming energy from the sun. So you can imagine that any distribution, dislocation, or latitudinal shifting of these wind patterns would have a profound effect on climate. So what about volcanic eruptions? We hear about these. They're catastrophic events, and they spew significant amounts of gases, CO2 and sulfur dioxide, etc., and ash into the atmosphere. This slide allows us to examine the effect these eruptions have on atmospheric temperature and climate change. Time is along the horizontal axis, and here we're spanning from 1950 to the present day. The vertical axis records changes in the average temperature of the Earth's atmosphere against an average temperature in the years 1880 to 1899. So there at zero, that's where we're starting off on, and what we're seeing is a change or a temperature anomaly with respect to that baseline. As we saw before, the average temperature of the atmosphere has been increasing since 1950, as shown by the red line. Imprinted on this increasing temperature trend is a series of zigzags. Now, when we impose the occurrence of major volcanic eruptions on this line, we see that really significant volcanic eruptions are associated with downward dips in the red trend. So what we're seeing is, here's Mount Agung in Bali in 1963-64, and we're seeing a sudden decrease in atmospheric temperature associated with that. But in a relatively short period of time, the temperature trend, the increasing temperature trend recovered, and then was hit again by the El Chichon eruption in Mexico in the mid-1980s, but it recovered again. And then Mount Pinatubo in the Philippines in 1991. Again, a significant but short-term decrease in temperature in the atmosphere, followed by a continuation in the temperature increase. So, although volcanic eruptions do affect the temperature in the atmosphere, we see that these effects are short-lived and don't affect the overall trend. Another effect, terrestrial effect, which can affect energy coming in from the sun, is what's called reflectivity or albedo, not libido, which is a completely different thing. While the physics is complicated, the idea is very simple. The more reflective matter you have on the Earth's surface, the more of the sun's energy is reflected back into space. Less clouds, less snow and ice, the more absorption of the sun's energy by the Earth's surface, and things heat up. The last terrestrial factor we'll examine is the atmosphere. Its makeup is important to the climate story. Today, the atmosphere is made up primarily of nitrogen, 78%, and oxygen, 21%, and a little argon, just slightly less than 1%. These three gases make up 99.93% of the dry gas volume of the atmosphere. Of the remaining trace gases, carbon dioxide is the most voluminous, making up about 0.03% of the total. But this is important. Carbon dioxide and some other gases produce a greenhouse or heat trapping effect due to the physical properties of their molecules, and we'll look at this in the second talk in this series. Changes in the amount of greenhouse gases in the atmosphere affect the heat trapping capability of the atmosphere. Another important atmospheric component is water vapor in the form of clouds, which can make up to 2% of the total atmospheric volume. Some other things can be entrained in the atmosphere. We saw volcanic ash. There's also dust, the amount of which is dependent on desertification and wind patterns. So we need to pay attention to atmospheric composition when thinking about climate change. Okay, so we've reviewed factors which can affect the Earth's climate. We looked at both extraterrestrial and terrestrial. And you can imagine that interaction between all these factors is complex. What we're going to do next is examine the geologic record for evidence of past climate change. You should be getting the idea that the Earth is dynamic and constantly changing, and that its climate should be no exception. Thus, we would expect that the Earth's climate has changed through time and still be changing due to natural processes. Before we begin to look at the geologic record of climate change, let's do a brief overview of concepts and terms. First of all, the geologic record, which consists of rocks and sediments and ice, contains information which tells us about climate in the past. Past climates are called paleoclimates. Paleos is Greek for ancient. So we're talking about ancient climates. Paleoclimate data allows us to see how changeable the climate has been in the past before man's appearance, and helps us determine what natural factors can affect climate change. Paleoclimate data are used as a foundation for climate scientists by providing crucial information such as magnitude and rates of past climate change. And computer models, which we hear about a lot, which are used to predict future climate patterns under varying scenarios, if these models don't match what's occurred in the past, then you'll have little confidence in their ability to predict what's happened in the future, what will happen in the future. So what do we use to determine past climates and study climate change through time? We only have actual measurements for the past 200 years. What do we rely on before that? What we do is we use what we call proxies. Proxies give indirect information about the climate, and they take a number of forms as shown in this slide. three types of proxies exist. Biologic proxies, such as tree rings, coral skeletons, plankton skeletons, shells, etc. The form and chemistry of these reflect temperature, atmospheric makeup, and in some cases, seasonality at the time the life form was living. Physical proxies are deposits such as sediment accumulations, the type of which reflect the climatic conditions at time of deposition. Examples are glacial boulder clay and glacial dropstones. They're all indications of the presence of ice. Chemical proxies, the last type of proxy, the ratio of certain elemental isotopes in molecules is affected by environmental factors such as temperature. One important example of this is the ratio between oxygen 18 and oxygen 16 in water molecules. In some places, the geologic record provides a sequential series of data or an archival record, which reflects changes in climate change through time. And we're going to look at some of these in detail. This slide shows the use of various proxies to determine climate information in the geologic record. As usual in this talk, time is along the bottom and the present is at bottom right. So going to the left, we're going backwards in time. The last 200 years, as indicated on this slide by the little thermometer, is the amount of time that we have actual climate records and temperature measurements for. Before that, we rely on proxies, biological, physical, and chemical, which we've just discussed. We have particularly good proxies for the past 800,000 years in ice cores, and I'll show you, we'll talk more about this later. Beyond 800,000 years, we rely on other proxies in the rock record, such as sediment deposits, fossils, etc. We see a decreasing resolution in our record as we go back through time, in major part due to increasing incompleteness of the geologic record with increasing age. The further back in time something was deposited, the more chance of it being eroded or destroyed due to geologic processes. The reason why this graph stops at 550 million years before present is because that's when multicellular life forms with skeletons and shells appeared in the geological record. And these shelly skeletons provide very useful proxy data. We do have some proxy data before that, but it's much more complex. In this slide, again, we show time on the horizontal axis. Again, we're looking at 550 million years from present. The vertical axis here on the right basically scales changes in oxygen 16, oxygen 18 isotope ratios. And this is a proxy for temperature change. What do we see in this slide? These two lines, the blue line and the black line, record changes in the ratio of oxygen 16 and oxygen 18 through time. First of all, we see we don't get a flat line. This indicates that temperature, as indicated by the proxy data, has been going up and down through time. The difference in smoothness of the black line and the blue line, they're based on the same data. It's due to a difference in the time window used for averaging the data. So it doesn't really matter. Basically, we're just showing, let's look at the black line and concentrate on it. Some important other things to notice. There are warmer periods and there are colder periods. Significant dips in the lines correspond to the cold periods and highs correspond to warm periods. Notice right now, we're in a pronounced cold period. Also noted on this slide is the occurrence through time of ice ages. And we can see there have been a series of ice ages through time. And look, guys, we're in the middle of one now. This graph shows the same data as the previous slide with some differences in how it's presented. To reflect increasing resolution of the geologic record as we reach near present time, the time axis is stretched out toward the right. And what I'm saying in here is each tick along here is equally spaced. But over here on the left, the time span between each tick is 100 million years. Then we go to 10 million years, 1 million years, 200,000 years, and then 5,000 years here. Also, what we've got is the vertical axes are temperature axes. The proxy data that we saw on the last slide, the 018, 016 proxy data, has been converted to actual temperature data. And the 0 in the temperature data is the average atmospheric temperature between 1960 and 1990. And we're here now, so it should be pretty close. The change in temperature should be pretty close to 0. But through time, we see in this line through here that temperature has been changing significantly through geologic time. Here are the ice ages that we saw in the last slide. As we noted, many of the cold phases are associated with ice ages, and we know they're ice ages because they're geologic deposits, which are demonstrably associated with ice activity occurring at these periods of time. One particular one, this one in the Permian about 300 million years ago, resulted in major life extinction events. During the Eocene, about 50 million years ago, the temperature was significantly warmer than today. And at that time, there were temperate forests growing in the Arctic archipelago. Since then, we've entered into our current ice age. When looked at in detail, where we have the data, i.e. especially in the last 5 million years, this right-hand part of the slide, the history of temperature change shows a multiplicity of zigzagging, recording temperature ups and downs on the longer trend. We're going to examine this trend in more detail. This is the same temperature data as in the past slide, but only for the past 5 million years. It's blown up so you can see the history more easily. There are a couple of important things to note, apart from the very jagged nature of the temperature line. First of all, the long-term trend of decreasing temperature, which we noted before. Secondly, the amplitude of the jaggedness and the temperature changes through time and gets more pronounced as we approach the present. And thirdly, there's a definite cyclicity to the jaggedness of the temperature record. If you compare the jaggedness between 2.5 million years ago and 900,000 years ago, there's about a 41,000 year cyclicity to this zigzagging, and that changes fairly abruptly about 900,000 years ago to a 100,000 year cycle. This lower graph, which is a blow up of the more recent part of the upper graph, most clearly shows the approximate 100,000 year periodicity to the zigzags over the last 800,000 years. You can see there's that cycle there is about 100,000, 100,000, 100,000, 100,000 years. So there's a remarkable cyclicity in here. So let's see where we get this evidence for. I mean, this is a pretty detailed information set or data set with regards to temperature change, in other words, climate change in the Earth over the last 800,000 years. Where do we get this from? And the answer is ice cores. This slide illustrates what ice cores are. The name says it all. They're cores of ice drilled from thick ice caps. These cores contain a near continuous record of snow accumulation through time. And if we go down to Antarctica, we can get ice cores of over 3 kilometers in length, which are almost continual record of snow accumulation during the last 800,000 years. Here is, you can see they've got these little, it's a little drill in here. It drills down, just literally coring the ice as it goes down, and they pull up the cores. This is a core. This lady's holding a core here. Here are some examples of the ice cores taken from different depths. This one here was taken from about 50 meters depth. This one at about 1,800 meters depth, and this one at over 3,000 meters in depth. Notice the distinct banding. If you look carefully on this one, you can see some banding. This is seasonal or annual banding in the ice cores. And when we look closely at the ice cores themselves, we see that they're full of little bubbles. And these are air bubbles which were trapped at the time of deposition of the snow. And we're able to get paleoclimate data from two sources within these ice cores. First of all, the air bubbles. We're able to do direct chemical analyses of the air bubbles to see what the chemical composition of the atmosphere was at the time of those air bubble entrapment. And secondly, the O16, O18 isotopic composition in the air and in the ice also affords an estimation of temperature, atmospheric temperature at the time. So these ice cores actually give us a remarkably detailed view of climate over the last 800,000 years. Where do they get these ice cores? This map on the top left is of Antarctica. The red circles are locations where ice coring has been done. This one, Vostok here, the picture below is the Vostok ice station. Doesn't look like a place you want to go to in your summer holidays. Set up to do Antarctic weather monitoring, but also a major core site for these ice cores. The second location, which is very important for ice coring, is the Greenland ice cap. So let's get back to the cyclicity of the temperature record, which we get from these ice cores. Here we show, we're looking at 450,000 years, the last 450,000 years. Again, we can see the approximate 100,000 year cyclicity of temperature change. And we can also see that there's repetition of the patterns within the cycles as well. Each cycle starts with a rapid and very significant warming. This warm phase is variably peaked, differences between different cycles. The warm phase may last between 5 to 15,000 years before a rapid cooling trend begins, which through a series of steps ends in a temperature minimum. The termination of the cycle occurs when the rapid warming phase of the next cycle begins. Climate science convention is to number things back from the present. According to this graph, we're in the early part of cycle 1. We're in the warm phase of cycle 1. The cool phases in each cycle are represented by accumulation and advance of glaciers, increase in size of ice caps at the poles and subpolar regions, and significant fall in sea level. The last glacial maximum or peak of ice ended at about 11,000 years ago with the sudden onset of present day, what's called Holocene warming. The times of relative warmth, these warm periods here, or interglacial periods, are relatively short. But take a look at the temperatures. You can see that the last one, about 120,000 years ago, had significantly warmer temperatures than what we're currently experiencing today. This slide is a map of the world showing ice extent during the last glacial maximum about 21,000 years before present. In other words, before the warming commenced 11,000 years ago, which caused retreat of the ice. You can see that much of North America and Northern Europe was covered by ice, as was the montane portion of South America and the mountainous parts of Australia and New Zealand. The warming phase that ended this last glacial maximum had profound effects on the animals living at the time, including humans. So what causes this climatic cyclicity? This is a subject of significant debate, but there is strong evidence that the perturbations in the Earth's orbit around the sun and around itself that we talked about earlier are a root cause. So let's remind ourselves of how much the Earth moves around itself and the sun, how much this will affect the amount of energy from the sun reaching the Earth. This little video portrays this quite nicely. On the left, we see obliquity or tilt. Remember, the axis of the Earth is tilted from vertical, and the tilt varies between 21.1 and 24.5 degrees. That variation is a 41,000-year cycle. In the middle, what we call eccentricity is the elliptical nature of the way the Earth moves around the sun. At times, it's very elliptical. At times, it's almost circular. And you can imagine that when at the far point of the ellipse, the Earth can be further away from the sun, thus receiving at that point in time less energy than it is when it's very close to the sun. And precession on the right, which is a 25,000-year cycle, is the wobbling of the Earth's axis. Altogether, these can be imagined to affect the amount of energy and where the energy from the sun comes in. This cyclicity, the cyclicity caused by these interacting movements was first emphasized by a man called Milankovitch, a Serbian mathematician who lived from 1879 to 1958. And Milankovitch dedicated his career to developing a mathematical theory of climate based on the resultant variations of solar radiation received by the Earth associated with these movements. The collective interaction of these planetary movements on Earth's climate history are now referred to as Milankovitch cycles. Yeah, it's hard to get your mind around some of this. So what I did is I put together this slide here, which is an attempt to show n members to illustrate the effect of on the energy from the sun reaching the Earth. The top diagram shows the maximum tilt of the Earth's axis at 24.5 degrees, associated with maximum eccentricity of the rotation of the Earth around the sun. The lower diagram shows minimum Earth tilt, 22.1 degrees, coinciding with minimum eccentricity or almost circular circulation of the Earth, or rotation of the Earth around the sun. On top of these two movements is imposed the third, precession, which is the wobble of the Earth. Together, these three factors affect the amount and angle of the arrival of the sun's energy on the Earth's polar regions. The upper setup here experiences greater hemispherical energy difference between what's called the perihelion, when the Earth is closest to the sun, and the aphelion, when the Earth is furthest away from the sun. So up here, maximum tilt and maximum eccentricity, you're going to get maximum changes in the amount of energy between this setup here and this setup here, whereas here, with minimum tilt and minimum eccentricity, you're getting much less variation in the amount of energy coming from the sun and where the energy is hitting the Earth. It's important to note that these Milankovitch cycles are not the only controls on climate and climate change, and there are many unanswered questions, but this Milankovitch cyclicity does appear to be a significant background driver to Earth climate change. Okay, to review, we've examined the factors affecting climate, and we've looked at the history of climate change on Earth. We've seen that climate, in the form of temperature of the atmosphere, is constantly changing, and recently at least has been doing so in a broadly predictable cyclic manner. We have some idea as to the drivers to this, but questions remain. We see that we're living in an interglacial warm period in the middle of an ice age. What we're going to do now is we're going to shift our focus from the geologic record to what's happening today. So what is happening today? As this graph illustrates, again, time at the bottom, going from 1880 to 2020, so 140 years. a temperature anomaly, basically relative to a set temperature occurring between 1951 and 1980. So that's set at 0. And what we can see is the relative change through time from that set 0 here. As we seen before, temperature is rising in the atmosphere. And since the late 1970s, the average global temperature, as recorded by a variety of independent organizations, has increased by almost 1 degree Celsius. Global warming is a fact. There we are. I said it. And basically, so where we're at is the end of this talk here. In the next talk, we're going to look at the potential causes for this recent warming and whether human activities may be responsible. This is where the real controversy lies. We're going to talk about greenhouse gases and other interesting things.